9.2 says, you know what? We can still use F equals ma even if we have a bunch of particles, as long as we know where the center of mass is of that particle. Okay, so I could have a problem like this and say, we've got, you're not on the board yet, sorry. Give me one sec, guys. I might have lost my screen mirror, and give me a second, but it's still going to work. It is nice. Okay, I got to reset my password. So in 9.2, it says like, hey, you know what? An object is fired, and it's moving, and it's moving, and it's moving, and then suddenly that object explodes. Okay, that object suddenly explodes. How can we follow its trajectory? How can we study it? Well, we can do the following. We can follow its center of mass the rest of the way. Sure, all these other particles are going off in random directions, and they're not random really, but in other directions. But the center of mass of all these particles, as all particles continue to go and spread out further and further as it's falling, the center of mass still follows the trajectory that the center of mass started on. And that's going to go into conservation, or that's going to come from really conservation of momentum, really, we're going to see. So 9.2 is simply saying that, you know what? This is true for a single particle. This is also true if we know that the center of mass is moving. That's COM, center of mass. So 9.2 literally does a whole derivation extending upon why you can use F equals ma for a particle system or for a bunch of particles, provided you know their center of mass. What else? That's pretty much it. I mean, this is still the overall force acting on it. This is, again, 9.2 that I'm talking about. This is still the overall force. So your book does an example where it's got like 3 particles, and each of them have a different force acting on them. Okay, so the forces look like that. Let me put another color so it shows that they're different. So each of the particles has a different force acting on it. And the key to this problem is to simply sum the forces in the x and sum the forces in the y. And then you can get the center of mass somewhere in between and figure out what happens to the center of mass. This is not one of your typical problems. This is, if anything, going to be maybe a multiple choice style problem. It's not going to be a part 2 style problem. But the idea behind it is that you can find all of these because you'd be given the values. Like this would be 2 newtons, maybe this is 3 newtons, this is 1 newton, this is an angle of 15 degrees, this angle here, let's say that's 25 degrees, the other one is acting straight down. So I could sum the forces in the x direction and use max, and sum the force in the y direction and use may. It's no different. It's not going to act any differently. The key is to recognize, though, that we find the center of mass and then behave and understand how the center of mass behaves as a result. So the center of mass might be a dot like, let's see, it's going to be shifting more to the right and slightly down. So probably like right here, I'll put an X. Okay, the X there in the middle of that diagram is what's representing the center of mass. So the center of mass will feel a force in the x direction and the y direction. And here we have to do 2 cosine 25 to go in for this force. This will be 3 cosine 15 to go in for this force. And this would be 0 because this is only in the y direction. And then the sum of the force in the y direction here, this will be 2 sine 25 minus 3 sine 15 because it's acting down and to the right, and then minus 1. Okay, those will give me the sum of the forces. And again, I would still be looking at the center of mass for this problem. And this is going to be, God bless. Oops. It's going to be a minus here because the forces in the y direction are acting downward. And again, there are 3 forces acting in the y direction, but only 2 of them are acting in the x direction. The yellow force is only acting in the y direction in the diagram there. What would the m value be? The m would be the total mass of the system, because we are looking at the acceleration of the center of mass. The acceleration of the center of mass. Your book does a ton with subscripts here, and it gets a bit cumbersome. This says the acceleration in the y direction, comma, for the center of mass. That's what this is saying right here. The acceleration in the x direction for the center of mass. So this m that's listed here is the total mass of the system. Your book uses a capital M to indicate that it's the total mass of the entire system there. So maybe a capital M for these two I'll change so you can see it. Okay, total M. So if you knew the mass was like, 2 kilograms, 1 kilogram, 4 kilograms, with those masses and all these positions, you can find the center of mass, which it really doesn't even matter the center of mass, where it physically is right now. We can figure it out so we know where it's headed. So if we knew the exact position of the center of mass, we could find the position of the system at some future time or at some future location because we know the overall force, and therefore we'd have the accelerations in both cases. Okay? My recommendation for this one is just look at the example. Read through the example on page 223. Okay, 223. I'm going to move on to 9.3, and I'm only moving on for the sake of time right now. I'm realizing more and more that we have to start speeding up if we're going to really get through all the material this year, so I don't want to get to the point at the end of the year. All right, we're stuck now. So again, that was page 223 you want to read. Let's look at 9.3 and 9.4 together. Now, 9.3 and 9.4 have two main overarching themes. The first concept is this. Momentum is conserved. Momentum is conserved. And it's not really introduced until you get to like section 9.5, I think, in your text. But that really does play a role. First, what is momentum? What is momentum the product of, I should say? Momentum is the product of mass times velocity. It's represented with a lowercase p, and that equals mv. The P, in case you're wondering why it's a P, maybe this help you remember, stood for anybody? I said it last year in class. That was density. That was density. Lowercase p stood for what? Leibniz termed this point, or coined this term. What did you say? Plumpness? No, not plumpness. It stood for progress. So Leibniz came up, think about it. Momentum. It's how much progress you're making. If you've got mass and you've got velocity, you're making progress. Have you ever been doing work and you're like, you're getting through your homework, right? It's the weekend, you're doing a lot of work, and you've got a good momentum going, you feel like you're in the flow. Have you ever said that to yourself? Like, I'm in a good flow right now. Like, I'm really doing good work, and I'm continuously doing, momentum. You're moving. Momentum. Yes, exactly what you should be doing. So momentum is mass times velocity here. Now, where does this play a role? Where does this play a role? What is velocity really when we think about derivatives, or what can we do when we consider this derivative here? What else can we say? The derivative of kinetic energy. It is actually. I never thought of it that way. It's really good, yeah. So kinetic energy in this, right, is 1/2 mv squared. If you take the derivative as a function of velocity, right? If you take the derivative ddv of this, it would become mv. Yeah, it's a really good point. I never even thought about that one. That's not one that's really talked about. Good point, Chip. What else? There's one more. Good, really good connection, Chip. What else?
Derivative changing position.
Changing position as a function of time. So you can think of this as p is also considered to be m times dx dt. Agree with that? And that's with time. So Chip did the derivative with respect to velocity, ddv. I'm doing ddt over here. Yeah?
It's like MA, but...
It is like MA, but give me more.
A, so it would be dA over dt, right? Or is we integrate it?
Good.
So it's integrate.
Yeah.
Integral of, I guess, would be delta V over delta T.
No, sorry. So the integral...
It's the integral of acceleration, right?
It is the integral of acceleration. Good. Which comes from what, though?
A equals delta V over delta T.
Good.
Or F equals MA.
Good. Yeah. So let's relate this to F equals ma is what I wanted to say. So let's relate to F equals ma. And let's think about that for a second. A, by definition, is really dv dt. Does everybody agree with that? Right? A is dv dt. So what else can we do? We can move this up. We could say F dt equals m dv. And then I can integrate both sides. And the integral of m dv, m is a constant, right? It's not my integration, it's not my variable of integration. M is a constant, so m comes out in front. The force is also a constant, or not, I shouldn't say that actually. The force is not a constant here. The force could be a function. Could be a function of time. But m is definitely a constant here. Well, for the AP exam, mass is not going to be changing as an object is moving. Should I say that right away? Let me hold off on that thought for a second. For now, we'll say it's a constant. But the integral of dv is v. And this is going to be v from the initial spot. Let's see. And this is going to be the integral of f dt, which makes this m times v minus v0 equals f dt. This means what? What does this mean down here? M times v minus v0. M times delta v. M times delta v. So Chris, I saw your hand, Chris. So Chris, could you tell me if it's m times delta v, what is that really? The change in progress. Good. Very good. So this leads us into 9-4. So the concept here of momentum being mv, right? Then we go through this whole process and show that, well, you know what? The change in momentum is equal to this. What is this? From last year. Both classes talked about it. But me and Mr. Donachik, I know you both talked about this concept. There's a concept that this is here. Some of you are not seeing it because it really is written as F times delta T in the past. It was F times delta T equals delta T. What is it? Impulse. Impulse. Remember the momentum impulse theory? The momentum impulse theory last year told us, well, you know what? If this F is a constant, we had this last year. F is not going to be a constant anymore. So we're going to go back to this one in a moment. That's really the one we're going to look at that is circled. But last year you had this, and then it was this. Which told us this, which in the very end became this. And this was last year's class that you learned at the bottom. F times delta T equals delta P. But really, the force felt on an object is not always going to be a constant. So, you know, what we do instead is we use what's circled up top there. The integral of force with respect to time is going to equal the change in an object's momentum. Is this on your form of the sheet?
Probably not.
Can we check? You should have it saved, right? In Notability, maybe? And that's just in the beginning of the year. Save that form of the sheet so you've got it in front of you. Somebody check and see, please, if what's circled or what's boxed, if either of them are on your form of the sheet. I think one of them is. I forget which one, whether the integral is or not. I assume the integral would be, because it is calculus form of the sheet, but
It would be lowercase p.
it would be a lowercase p.
Momentum's on the p impulse. It says it's on the J equals integral of f respected dc equal.
Where is that? On the top, bottom?
It's the sixth one.
Oh, it's all the way up here.
Yeah.
There it is. Okay. J is impulse. J is listed as impulse on your form of the sheet. So look for J equals this, which equals delta P. That's on your form of the sheet. It's toward the top. Okay, so it's given. So you don't have to put it in your calculator. But you know what? What does this tell us? If the change in momentum equals the integral What kind of a problem are you going to be looking at? Multiple choice wise. What do you think?
A graph.
A graph. Thank you, Spence. What else?
Another graph of like different variables to then get there.
Okay. More than just a graph then? A graph or a equation or function. Very good. Most likely, when it comes to the momentum impulse theory on multiple choice, you should be ready to be able to read a graph and look for the what under the curve. Look for the area under the curve to calculate the impulse. And once you have the impulse, you'll know the change in momentum. So if you have the initial momentum, or if you have the final momentum, you can calculate the other of the two if you have the overall impulse felt, which is the area under the F versus T graph. Okay, the area of the F versus T graph. What else? How about this last statement? Let's write down. So those are the really big statements right there so far. Let's write down one more statement here. I'm going to go to the next slide. Let's jot down this fact that we could say that if P is equal to mv, then F is going to equal the derivative of P, which equals the derivative of mv, which is really ma. The key is boxed in, the important part is boxed in red here, but just to show you why this is true. F is equal to the derivative of your progress or of your momentum, and your momentum is mv. The derivative of mv, m is a constant, it comes out in front. The derivative of v is a, so you get ma. This comes back to, again, F equals ma. This is really, again, F equals ma. So technically speaking, you could be given a graph of P versus T, where this is not power, but momentum. And I might be able to tell because the units would say kilograms times meters per second. What would the units of power say? Power is the y-axis, really. What would it be? Watts. Okay, so if we see P, we know either it's momentum or power. Obviously, if it's lowercase, it's obvious, but it may not look like a lowercase. It may look like an uppercase depending upon a graph. So use your units to help you to recognize what it is. Most likely the problem will say the momentum of a function of a particle is plotted as a function of time. So you'll know it's momentum. So as a result, if you were given this kind of a problem, okay, something like that, you could be asked many different types of questions. When is the force felt on this object positive? When is the force felt on this object positive? When in these regions? Chris, tell me, starting here. Is it positive here?
Yeah.
Until when, Chris? Tell me when to stop.
Until there.
Okay, then what's the force from this point on?
Zero.
Zero force, because what is he taking? He's looking at the what of the graph? The derivative, which is really the slope. Slope. Derivative is slope. Derivative is slope. So the derivative is positive, the derivative is zero, then the derivative is?
Negative.
Until it gets to?
There.
And then the derivative is?
Zero and this changes to
Positive,
positive.
then negative, then zero, then kind of positive at the end. Ish. I like that. Last thing to leave you with, that's the graph of that one. The other graph that we're going to again be focused on is going to be this one right here. Okay, and from this one, what can we determine? We can, instead of finding slope at any given point, like we did here, slope, 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 we did all those slopes. Here we can find the area under the curve. And the area under the curve there of F versus T, that area will give me the change in momentum of an object. Those are the two things we really want to consider when it comes to the additional calculus portion of this part of physics. 9.3 and 9.4. Okay, so here's what I'm going to do. I'm going to give you some homework. I have the assignment written already. I was locked out of Moodle over break and I changed my password. So I changed it already this morning. We're fine. So give me like 10 minutes to put the homework up on Moodle so you can see it. It'll be homework from 9.1, 9.2, and 9.3. Okay, listed partially. You should be reading. Part of it multiple choice. Part of it homework assignments. And I'll put the problem set up for that. They're all written, but I'll put them all up. So it'll be 9.1, 9.3, and 9.4. I don't give you homework assignments from 9.2. Okay, I didn't give you one from 9.2. My recommendation is that you read page 223 from 9.2.
Yeah.